Hi, welcome to this video on topic 12 of Edexcel A-level chemistry, acid-base equilibria. Enjoy! Let's start by looking at the difference between an acid and a base. The definition of a Bronsted-Lowry acid is a proton or H+ ion donor, whereas the definition of a base is a proton acceptor. Bases are able to do this because they have a lone pair of electrons that is available to form a dative covalent bond. Acid-base reactions involve the transfer of protons. It is easy to see this in this equation. The relationship between an acid and its corresponding base is known as a conjugate acid-base pair. In the equation above, the ammonium ion and ammonia are one acid-base pair, and the hydroxide ion and water are another acid-base pair. Molecules with both acidic and basic properties are known as amphoteric, for example, water. Now let's look at the difference between strong and weak acids. To do this, we need an understanding of the term dissociation. Dissociation is when an acid dissolves in water and separates either partially or completely into its ions. Strong acids will always dissociate completely, whereas weak acids will only partially dissociate. Strong acids include hydrochloric acid, sulfuric acid, and nitric acid. Carboxylic acids are a good example of a weak acid. It is important to note that the strength of an acid is not related to concentration, which just explains how diluted a solution is with water. The pH scale is a logarithmic scale ranging from 0 to 14 that indicates the strength of an acid or an alkali by showing hydrogen ion concentration. pH can be calculated using the equation minus log to the base 10 of hydrogen ion concentration. This equation can be rearranged as shown. A low pH indicates a high hydrogen ion concentration, whereas a high pH indicates a low hydrogen ion concentration. A difference of 1 on the pH scale indicates a tenfold difference in hydrogen ion concentration. The pH scale is only accurate for dilute solutions, that is, of a concentration of less than 1 molar. You may be asked to calculate the pH of a strong acid. To do this, you need to assume that the hydrogen ion concentration is the same as the concentration of the acid if it is a monoprotic acid, or the hydrogen ion concentration is the same as 2 times the concentration of the acid if it is a diprotic acid. This is because strong acids fully dissociate in water to form hydrogen ions. Let's take a look at this example question. What is the pH of 0.2 molar HCl? First, we need to assume that the hydrogen ion concentration is equal to the concentration of HCl, which is 0.2 molar or 0.2 moles per dm cubed. Then we substitute this into the equation for calculating pH, and we get a pH of 0.7. Here is another question to have a go at. What is the pH of 4.8 times 10 to the minus 4 molar H2SO4? Sulfuric acid is a diprotic acid, so we need to times the concentration of the acid by 2 to get the concentration of hydrogen ions. Then substitute this number into the pH equation and whack it in your calculator to get the answer. You should get a pH of 3.02. Calculating the pH of weak acids is a bit more tricky. You need to use Ka, the acid dissociation constant. This equation shows the dissociation of ethanoic acid. Ka here would be the concentration of the ions at equilibrium divided by the concentration of ethanoic acid at equilibrium. Notice that water is not included in the Ka equation because the concentration of water remains constant. The units for Ka are moles per dm cubed. A high Ka value indicates that the equilibrium for the acid dissociation equation lies to the right, whereas a low Ka value will indicate that the equilibrium lies to the left. Let's have a go at this example question. I like to start by writing out the equation of the dissociation of the acids that we are working with, in this case ethanoic acid. Then I use this to write out the Ka equation. In order to calculate the pH of ethanoic acid, we do need to make some assumptions. Firstly, we need to assume that the concentration of hydrogen ions is the same as the concentration of ethanoate ions. We also assume that the concentration of ethanoic acid at equilibrium is the same as its original concentration. Using this and the information in the question, we can calculate the pH of ethanoic acid. Here I am substituting 1.7 times 10 to the minus 5 in place of Ka in the Ka equation, and 0.01 in place of the concentration of ethanoic acid at equilibrium. I have squared the concentration of hydrogen ions since hydrogen ion concentration equals ethanoate ion concentration. Now it's just a case of working it through. So you times the 1.7 times 10 to the minus 5 by 0.01, then you square root to get the hydrogen ion concentration. Then substitute this into the pH equation and bung it in your calculator to get an answer of 3.38. Sometimes you may be asked to convert Ka into pKa, which is easy using this equation. It may be useful to know that the higher the value of Ka, the smaller the value of pKa, and vice versa. Before we can calculate the pH of bases, we need to understand the concept of the ionic product of water. Water can dissociate to form hydrogen and hydroxide ions. Since this reaction is endothermic, the equilibrium lies to the left. Therefore, the concentration of H2O remains relatively constant. If we wrote a Kc expression for this equation, it would look like this. However, we do not include H2O because its concentration remains constant. So we end up with this new expression where the equilibrium constant equals the concentration of hydrogen ions multiplied by the concentration of hydroxide ions. This is known as the ionic product of water and is identified by using Kw rather than Kc. The units for Kw are moles squared dm to the minus 6. At 298 Kelvin, the value for Kw is always 1 times 10 to the minus 14. pKw can be calculated in a similar way to pKa. Using this knowledge, we can now calculate the pH of strong bases. Strong bases will fully dissociate in water to form OH- ions. Let's have a go at this example question. What is the pH of 0.02 molar KOH? I like to start by writing down the equations that I know I'm going to need. So here I've written the pH equation and also the ionic product of water. Since potassium hydroxide is a strong base, we know that it will fully dissociate. Therefore, the concentration of hydroxide ions is the same as the concentration of the acid. I should have made it clear in the question that the temperature is 298 Kelvin, and therefore Kw equals 1 times 10 to the minus 14. We can now work out hydrogen ion concentration by rearranging the Kw equation. And that gives us 5 times 10 to the minus 3 moles per dm cubed. Now we plug this value into the pH equation and that gives us a pH of 12.3. Lastly, let's look at acid-base titrations. This example question says calculate the pH of the solution formed when 25 centimeters cubed of 0.25 moles per dm cubed of H2SO4 is added to 100 centimeters cubed of 0.2 moles per dm cubed NaOH. First, we must calculate the moles of hydrogen ions and the moles of hydroxide ions and work out which one is in excess. In this case, OH- is in excess. Then we need to calculate the number of excess moles. We do this by subtracting one value from the other. Next, you need to work out the concentration of the thing you have in excess, in this case OH- ions. However, in other questions it may be hydrogen ions. So to do this we use moles divided by volume. We have 0.0075 moles, and for the volume we need to use the entire volume, which means you need to add the two volumes of the acid and the alkali together. And that gives us 0.06 moles per dm cubed. Step number 3 is to use this value to calculate the concentration of hydrogen ions. We need the concentration of hydrogen ions to work out pH. Then we plug this value into the pH equation. And that gives us a pH of 12.78. Well, that's it for this video. I hope you enjoyed.